Our daily lives depend on a reliable road infrastructure. Yet, as with many other things, we often take the roads for granted. Growing population, heavier road traffic, and increasing number and severity of extreme weather conditions resulted in stricter sustainability standards and more comprehensive greenhouse gas emission limits. These changes provide us with an opportunity to rethink the future of the paving technologies. HiMA, or highly modified asphalt, is a paving technology developed to address the needs of modern pavement infrastructure. Yet, why should you be interested in HiMA? How does it really work? And most importantly, is it a proven technology? Let's start with answering the why question. Investing in pavement infrastructure usually takes into consideration the life cycle cost of an asset. Simply put, the life cycle cost is the cost of initial construction, as well as any subsequent maintenance expenses and salvage value, all discounted to present. The HiMA technology has been shown to reduce the pavement life cycle cost. The cost reduction may be achieved in two ways. The first option is to make the initial pavement thinner, thus saving on the cost of materials. The second option is to retain the original pavement thickness and instead rely on the improved performance to extend the pavement life cycle. Sometimes, specific pavement issues take precedence over the life cycle cost consideration. HiMA excels at addressing severe rotting pavement problems by delivering extra material strength. The continuous polymer network helps to eliminate or minimize top-down and bottom-up fatigue cracking. Additionally, the HiMA-enabled asphalt mixtures may drastically eliminate or reduce a wide range of issues including reflective cracking, studded tire damage, extra heavy load damage, delayed post-construction opening time, raveling of open-graded asphalt, water damage, curb reveal or road clearance height issues, and problems related to providing sufficient pavement structural support over sensitive utilities beneath. Although reducing the life cycle cost of an asset is important, HiMA may also be beneficial to the environment. Using fewer raw materials and reducing the number of repair and maintenance cycles may have a profound impact on the carbon footprint of a pavement asset. The initial material carbon footprint of HiMA may be somewhat higher when compared to the conventional solutions. However, fewer maintenance and reconstruction operations may allow for a lower overall life cycle carbon footprint of HiMA pavements. Consequently, our society can benefit from lower long-term infrastructure spend and fewer hours lost in traffic jams due to road repair. Let's now discuss how HiMA enables the mentioned benefits. HiMA should really be understood on two distinct levels, the asphalt level and the bitumen level. This is a schematic illustration of a conventional SBS polymer. The solid blocks on both ends allow the polymers to assemble together in bitumen. They also give the PMB its strength. The rubber segment in the middle makes the PMB elastic and resilient to cracking. The durability of the polymer network grows as the dosage of the polymer in bitumen increases. In this demo, the polymer-modified bitumen samples containing different SBS dosages were subjected to a creep test at a room temperature. Increasing the polymer concentration visibly led to significant gains in the material strength. This phenomenon is often characterized using an S-curve analogy. In the lower part of the S-curve, the material acts as a traditional polymer-modified bitumen. However, as the polymer concentration increases to approximately 7 to 8% SBS, the material reaches the upper plateau of the curve. In that region, the material starts acting like an elastic band, reaching the continuous polymer network effect. Achieved at a typical SBS concentration of 7 to 8% is very difficult while using the conventional SBS polymers. The very high material viscosity prohibits normal operations of the PMB and asphalt plants. Additionally, the asphalt mixture workability becomes very challenging. To enable the high levels of modification in the paving applications, Kraton invented a new type of SBS polymer. The unique design enabled faster dissolution time in bitumen, enhanced cross-linking capabilities, and ultimately a lower viscosity of the polymer-modified bitumen. The unique nature of Kraton's polymer enables creating a dense continuous network necessary to achieve a step change in material performance. This simple demonstration visualizes the strength and the elasticity of bitumen with the continuous polymer network, the kind achievable with the HiMA technology. Although enabled by Kraton's polymers, the HiMA technology itself is not proprietary. Numerous construction material companies implemented HiMA into their product offering. Additionally, a growing number of public agencies used HiMA to improve their infrastructure while utilizing the existing specifications frameworks. However, as with any novel technology, the conventional test limits are often inadequate to properly capture the HiMA PMB unique characteristics. Polymer network is at the core of the HiMA technology. MSCRT, or Multiple Stress Creep Recovery Test, is a convenient surrogate tool for evaluating the polymer network quality in bitumen. Dynamic shear rheometers used to perform the test are sensitive to even small differences in the material performance. HiMA PMBs are typically tested at 76 degrees Celsius and a 3.2 kilopascal stress level, with a specified minimum 90% recovery. At these conditions, only the PMBs with a continuous and robust polymer network can pass the limit. The HiMA PMBs are also specified with a maximum viscosity limit, yielding a material that balances both the material performance and workability. What happens at the bitumen nanoscale has a set of very profound effects on the asphalt performance. Asphalt mixture design is an act of balancing the rutting and the fatigue resistance. Improving one parameter typically comes at the cost of deteriorating the other. The concept of the balance mix design may help to reach an appropriate balance. Nevertheless, making incremental adjustments to the aggregate gradation or the bitumen content has its limits, especially when the pavement structure must be thin or is subjected to a heavy traffic. Conventional polymer modified bitumen offers an excellent but limited solution to this problem. The HiMA technology offers a more powerful solution to easily address both fundamental distresses at the same time. To illustrate the unique capabilities of the HiMA technology, we've prepared a set of demonstrations utilizing small asphalt mastic specimens. The specimens were made with 90% washed sand and 10% bitumen by weight. Each demonstration features 3 specimens. The first made with a conventional paving bitumen, the second utilizing a 3.5% SBS polymer modified bitumen, and the third made with a highly modified bitumen. The first demo was conducted in an environmental chamber at 60 degrees Celsius. Each specimen was loaded with 100 gram weight. Despite the same aggregate and bitumen content in mastic, the HiMA's continuous polymer network provided a visible improvement in terms of the permanent deformation resistance. At the intermediate temperatures, where the load-induced fatigue cracking usually occurs, the HiMA polymer network allowed for asphalt to reliably recover after flexing. This helps minimizing the crack formation and propagation. The third demonstration concerns the durability of pavements built with HiMA technology. A golf ball falling from a set height will impact each of the 3 specimens. Both the unmodified and the conventional PMB specimens did not survive the impact. The ability of the HiMA to withstand the impact highlights the unique capabilities of the continuous polymer network. As compared to the unmodified bitumen, the conventional PMBs allow for a step-change improvement to asphalt rotting and fatigue performance. HiMA, with its fully continuous polymer network, take these improvements to the next level. Any comprehensive HiMA technology coverage requires addressing the aspects of asphalt mixture production, paving, and opening to the traffic. The low viscosity nature of the HiMA technology allows for asphalt mixture production process that is similar to that of the conventional PMB mixtures. Additionally, it is possible to produce HiMA mixtures with significant quantities of reclaimed asphalt. HiMA asphalt is relatively easy to handle. The conventional Warmix asphalt technologies can be further used to improve the mixture workability and reduce the production and paving temperatures. After placement and compaction, HiMA mixtures reach the conventional asphalt stiffness at a relatively higher temperature. This characteristic may allow for faster opening to the traffic without risking premature pavement deformation. So far, it's been explained why and how to use the HiMA technology. The third question, perhaps the most pertinent one, remains unanswered. Has HiMA been shown to work in real pavements? To answer this last question, we need to move back to year 2009, when the first HiMA test section has been built at the National Center for Asphalt Technologies in Opelika, Alabama. The Kraton HiMA test section was constructed next to a reference section made with a conventional PMB. The study aimed to demonstrate that it was possible to make asphalt pavements thinner and more resistant to cracking and permanent deformation at the same time. Both test sections were subjected to 20 million equivalent single axle loads over a course of 5 years. Despite being 18% thinner than the conventional PMB test section, HiMA resulted in 70% less rotting and no bottom-up fatigue cracking, while the control conventional PMB section resulted in 18% of area cracked. In 2010, at the Napier port in New Zealand, HiMA was used to successfully address severe rotting issues stemming from extra heavy container handling equipment. In 2012, HiMA emulsion was substituted for latex-modified asphalt emulsion in the microsurfacing of 4.5 lane miles of local streets in Dallas, Texas. That same year, the Oklahoma Department of Transportation used HiMA to address severe rotting issues related to poor soil conditions on the I-40 highway. In New York City, HiMA thin overlay was used on 53 blocks of Manhattan's First Avenue, which required minimal adjustments of drainage inlets. The Viracopos Airport in Brazil benefited from HiMA's superior load-bearing capacity, allowing for a substantial reduction of the taxiway wearing course thickness. In the Brazilian state of Santa Catarina, HiMA helped avoid the full pavement reconstruction. Instead, the top 2 layers were replaced with HiMA at a fraction of the cost. On the US 90 in Midway, Florida, heavy traffic next to a large truck stop was causing severe rotting issues. A HiMA friction course helped to address the problem in a simple and quick manner. A regional road administration in Katowice, Poland, successfully piloted HiMA, searching for a more sustainable and affordable pavement technology. The MS3 bridge in Ostróda, Poland, features a unique use of HiMA binder in mastic asphalt bridge deck application. In Anchorage, Alaska, HiMA helped to address the rotting problems caused by studded tires, which are commonly used during the winter time. A Tampa field study, conducted by the Florida Department of Transportation, has shown that HiMA was successful in reducing the occurrence of concrete joint reflective cracks and rotting in the asphalt overlay. In 2018, the HiMA technology was used on a tollway in Rajasthan, India, to protect the asset from damage related to extremely heavy traffic and occasional flooding. In 2018 in Prague, a damaged runway was repaired with HiMA while the airport was in operation. As of late 2020, all the mentioned pavement projects continued to provide excellent performance. Whether solving a particular performance-related problem or lowering the life cycle cost, the HiMA technology can provide a unique value proposition in a broad variety of pavement assets. With well over 5 million mixed tons paved and in use around the world, HiMA is not a fad. Rather, it's a proven and reliable technology. It is crucial to recognize that the progress achieved by HiMA would not be possible without the active adoption and participation in this technology by the innovative material and construction companies, the forward-looking road owners and public transportation agencies, as well as the academic institutions, all of whom had a unique and thorough impact on promoting the HiMA technology. If you think that the HiMA technology could benefit your business or improve your asset's value, but are not sure where to start, you're in the right place. In addition to supplying the specialty polymers for the HiMA technology, Kraton provides comprehensive support for parties interested in adopting HiMA. Kraton's bitumen innovation centers, located in Amsterdam, Houston, and Mumbai, provide HiMA PNB formulation and testing assistance. Kraton's commercial and technical team possesses experience and knowledge helpful in tailoring the HiMA technology to very specific project needs. Thank you for your attention, and please make sure to get in touch with us during the E&E Congress.